In this video, I will explain to you what a diode is, how it is constructed, and how it works. Let's start the video. Welcome to Star Technology 5G. A diode is a semiconductor device that allows current to flow easily in one direction, but severely restricts current from flowing in the opposite direction. Diodes are also known as rectifiers because they change alternating current into pulsating direct current. Diodes are rated according to their type, voltage, and current capacity. Diodes have polarity, determined by an anode lead and cathode lead. That is a standard diode symbol. In the symbol, we can see that there are two terminals. This terminal is called the anode. The other one is called cathode. The arrowhead is the anode that represents the direction of the conventional current flow in the forward biased condition. A diode conducts electricity primarily in one direction. It has high resistance on one end and low resistance on the other end. A diode is made from a small piece of semiconductor material, usually silicon, in which half is doped as a p-type and half is doped as an n-type. The p-type is called the anode and is connected to a positive terminal. The n-type is called the cathode and is connected to a negative terminal. P-type and n-type semiconductors. Semiconductive materials like silicon and germanium do not conduct current well. This is because of the limited number of free electrons in the conduction band and holes in the valence band. The atomic structures of silicon and germanium are shown in the figure. Both silicon and germanium have the 4 valence electrons. The valence electrons in silicon are in the 3rd shell closer to the nucleus, and in germanium are in the 4th shell. This means that the germanium valence electrons are at higher energy levels. Therefore, require a smaller amount of additional energy to escape from the atom. This property makes germanium more unstable at high temperatures and results in excessive reverse current. This is why silicon is a more widely used semiconductive material. Intrinsic silicon, or germanium, must be modified by increasing the number of free electrons or holes to increase its conductivity and make it useful in electronic devices. This is done by adding impurities to the intrinsic material. This process is called doping. This process introduces two types of impurities, p-type and n-type. The difference between n-type and p-type semiconductors is the primary material used to create the chemical reaction during doping. Depending on the material used, the outer orbital will have either 5 or 3 electrons, making one negatively charged, n-type, and one positively charged, p-type. What are p-type semiconductors? To increase the number of holes in intrinsic silicon, trivalent impurity atoms are added. These are atoms with 3 valence electrons such as indium. Each trivalent atom forms covalent bonds with 4 adjacent silicon atoms. All 3 of the indium atoms' valence electrons are used in the covalent bonds, and, since 4 electrons are required, a hole results when each trivalent atom is added. Because the trivalent atom can take an electron, it is often referred to as an acceptor atom. The number of holes can be carefully controlled by the number of trivalent impurity atoms added to the silicon. This material is called p-type semiconductor. Majority and minority carriers. In p-type material, most of the current carriers are holes. Silicon atom doped with trivalent atoms is called a p-type semiconductor. The holes are the majority carriers in p-type material. There are also a few conduction band electrons that are created when electron-hole pairs are thermally generated. These conduction band electrons are not produced by the addition of the trivalent impurity atoms. Conduction band electrons in p-type material are the minority carriers. What are n-type semiconductors? To increase the number of electrons in intrinsic silicon, pentavalent impurity atoms are added. These are atoms with 5 valence electrons such as antimony. Each pentavalent atom, antimony, in this case forms covalent bonds with 4 adjacent silicon atoms. 4 of the antimony atoms' valence electrons are used to form the covalent bonds with silicon atoms, leaving 1 extra electron. This extra electron becomes a conduction electron because it is not involved in bonding. Because the pentavalent atom gives up an electron, it is often called a donor atom. The number of conduction electrons can be carefully controlled by the number of impurity atoms added to the silicon. A conduction electron created by this doping process does not leave a hole in the valence band because it is in excess of the number required to fill the valence band. So this type of material is called N-type semiconductor. Majority and minority carriers. In N-type material, most of the current carriers are electrons. Silicon doped with pentavalent atoms is an N-type semiconductor. The electrons are called the majority carriers in N-type material. Although the majority of current carriers in N-type material are electrons, there are also a few holes that are created when electron-hole pairs are thermally generated. These holes are not produced by the addition of the pentavalent impurity atoms. Holes in an N-type material are called minority carriers. P-N junction. A p-type material consists of silicon atoms and trivalent impurity atoms. An impurity atom releases holes when it bonds with silicon atoms. However, since the number of protons and the number of electrons are equal throughout the material, there is no net charge in the material, and so it is neutral. An N-type silicon material consists of silicon atoms and pentavalent impurity atoms. An impurity atom releases an electron when it bonds with silicon atoms. Since there is still an equal number of protons and electrons, including the free electrons, throughout the material, there is no net charge in the material, so it is neutral. If p-type and n-type semiconductors combine, a p-n junction is formed. A boundary between them would severely inhibit its utility by scattering the electrons and holes. The term junction refers to the region where the two regions of the semiconductor meet. It can be thought of as the border region between the p-type and n-type blocks. When the p-n junction is formed, n-type electrons begin to flow into the p-type semiconductor. That is, as the atoms lose charges, areas with non-mobile charges are produced. This event continues until a charge balancing occurs. The flows of these majority carriers in the semiconductor will affect the region around the junction. A positive charge migrates to the n-type side of this region, and a negative charge migrates to the p-type side. The region in between, which consists of the combination of p-type and n-type semiconductors, is called the depletion region. In this region, an electric field from n-type to p-type is formed, which stops the carrier flow. This electric field is called barrier potential. The magnitude of the barrier potential here depends on the doping materials and semiconductors used. If the semiconductor material is silicon, then its voltage is 0.7 volts, and if the semiconductor material is germanium, then its voltage is 0.3 volts. To provide electrical connection, two metal caps are fitted at both ends to which the lead wires are joined. Forward bias. When the n-type semiconductor material is connected to the negative terminal of a battery and the p-type semiconductor material is connected to the positive terminal of the battery using the resistor. The resistor is used to limit the forward current to a value that will not damage the diode. This condition is called forward bias. To flow the current through the diode, the forward voltage should be higher than the barrier potential voltage. If the diode is made from germanium, then the barrier potential is 0.3 volts. And if a diode is made from silicon, then the barrier potential is 0.7 volts. For example, if this diode is made from silicon, we would need more than 0.7 volts. When battery voltages are greater than barrier potential, the holes in the p-type region and the electrons in the n-type region are pushed towards the junction. The positive charge applied to the p-type material repels the holes, while the negative charge applied to the n-type material repels the electrons. As electrons and holes are pushed towards the junction, the distance between them decreases. This lowers the barrier in potential. With increasing forward bias voltage, the depletion zone eventually becomes thin enough that the zone's electric field can't counteract majority charge carrier motion across the p-n junction, consequently reducing electrical resistance. The electrons, or holes, which cross the p-n junction into the p-type material, or into the n-type material for holes, will diffuse in the near-neutral region. Therefore, the amount of minority diffusion in the near-neutral zones determines the amount of current that may flow through the diode. Actually, holes do not move when the electron jumps from one energy level to another. He left one hole. The previous electron jumped and filled this hole. This process continues, and electrons jump from one hole to another. VI characteristic for forward bias. If we show the VI characteristic curve for a forward bias diode, in the vertical axis that is the forward bias current IF, and along the horizontal axis that is the forward bias voltage VF, when zero voltage applied across the diode there is no forward current. When forward bias voltage increase there is forward current. As gradually increase the forward bias voltage, the forward current and the voltage across the diode gradually increase. When the forward bias voltage is increased to a value where the voltage across the diode reaches barrier potential, approximately that voltage is 0.7 volts. As you continue to increase the forward bias voltage, the current continues to increase very rapidly, but the voltage across the diode increases only gradually above 0.7 volts. This small increase in the diode voltage above the barrier potential is due to the voltage drop across the internal dynamic resistance of the semiconductive material. Reverse bias. When the N-type semiconductor material is connected to the positive terminal of a battery and the P-type semiconductor material is connected to the negative terminal of the battery. This condition is called reverse bias. Because the P-type material is now connected to the negative terminal of the power supply, the holes in the P-type material are pulled away from the junction, causing the width of the depletion zone to increase. Similarly, because the N-type region is connected to the positive terminal, the electrons will also be pulled away from the junction. Therefore the depletion region widens, and does so increasingly with increasing reverse bias voltage. Now there is only very small reverse current flow from the diode. VI characteristic for reverse bias. When a reverse bias voltage is applied across a diode, there is only an extremely small reverse current through the p-n junction. As gradually increase the reverse bias voltage, there is a very small reverse current and the voltage across the diode increases. When the reverse voltage across the diode reaches the breakdown value, the reverse current begins to increase rapidly. As you continue to increase the bias voltage, the current continues to increase very rapidly, but the voltage across the diode increases very little above breakdown, with exceptions, is not a normal mode of operation for most p-n junction devices. Thank you for watching. Please subscribe to Star Technology. Please like and share the video.